Thank you. So this talk was supposed to be given by Sungjae Lee, but he couldn't make it, so I'm replacing him. This work was based on recent work with Jimbom Bae, who is our postdoc, and Sungjae is our new faculty member at KIAS. Right, so let's start with 3D gravity, pure gravities. Now, this action is very well known from early 80s. And we are interested in the theory in 3D with negative cosmological constant. And this theory has no propagating degrees of freedom. And so there's no dynamics. And perturbatively is finite. You can do perturbative expansion, but from the structures of theory that any divergence, if it's there, can be removed by change of cosmological constant and also by redefining metric tensor. So this theory seems to be trivial. So maybe quantum gravity is again almost straightforward. However, there are two surprises in this series. First of all, there is discovery of black holes in this theory by three gentlemen in early 90s. And these black holes are massive and has angular momentum and also finite size horizon with non-trivial entropies. And especially this 3D gravity can have additional variation without high additional variation, which is 3D Chern-Simons terms, gravitational Chern-Simons terms. However, we are interested in this talk in the case where there's no such a term, which means that some theory is parity even. Without this 3D gravitational Chern-Simons term, there is no gravitons. So these entrophies, we introduced CL and CR for later reasons, but basically given in terms of size of event horizon R plus and also R minus, two parameters, and then gravitational constant and cosmological constant. Now, second surprise was discovered earlier, late 80s. This theory with negative cosmological constant has asymptotic Virasoro algebras, which means that if you, even though theory itself is trivial, if you quantize the theory with certain AdS boundary conditions, then there are remaining degrees of freedom, and that allows us to have two copies of Virasoro algebras. And that will act on the Hilbert space. And it is some sense precursor to AdS-CFT correspondence. So it seems that 3D pure gravity with negative cosmological constant is a lot more interesting than simple trivial theory. So question is, can 3D gravity exist as a constant quantum theory, both perturbatively and non-perturbatively? Now, pure 3D gravity, solving the quantum gravity in AdS space is equivalent to finding the dual CFT on the boundaries of AdS3. Now, to attack this problem, Witten and Maloney was trying to define the thermal partition function of 3D gravity in AdS3 space. Now, assumption Witten has introduced is that dual CFT factorizes into holomorphic CFT and anti-holomorphic CFT. And today we'll just focus on the holomorphic part of the CFTs. And holomorphic factorization plus modular invariance implies that central charge has to be 24 times K. Both left moving and right moving central charge are identical because there is no gravitational Chern-Simons terms. And also, this means that cosmological constant or AdS length parameter is quantized in unit of Newton constant. And also, this modular invariance implies the partition function, this holomorphic part of partition function should be periodic, which implies that all the operators has to have an integer conformal weight. And then BTG black holes, mass and angular momentum are quantized in AdS units. Now you look at the vacuum contribution and to the this partition function, and if you look at that, then one can, it's made of the vacuum energy contributions plus Virasoro descendant, and this product comes from n equal 2 as vacuum is invariant on the SL2Z, SL2 Virasoro subalgebras. So this n from n equal to 2 to infinite comes from the Virasoro contribution of the Virasoro descendant, and also that can be identified as a boundary graviton discovered by Brown and Hanov. So one could regard that as a perturbative state correction due to perturbative state at 3D gravity living at the boundaries. And that can be again regarded as a one correction coming from perturbative expansion around AdS vacuum ground. But as we know, that's not the end of the story. This vacuum n is Virasoro descendant doesn't give you partition function, which is invariant on the modular transformation. As we said before, there are other states in 3D gravity, which is BTG black holes. And those are sort of non-perturbative state. And from a classical point of view, these BTG black holes have a positive mass, which is bounded by absolute value of angular momentum. And angular momentum is, again, non-negative. Its absolute value is non-negative. So if we exclude the black holes of zero horizon and zero entropy with some sense massless black holes, then one can see that this non-perturbative correction of BTG black hole will give a correction to a partition function as order Q, because L0 will have a non-zero, non-negative contributions. And for these quantized corrections, the entropy will be given in this formula. So full partition function of the pure 3D gravity will be given in terms of vacuum corrections plus correction from BTG black holes. And also is Virasoro descendant. Now, these theories are, some sense from boundary point of view, these theories are called the extremal conformal field theories, in the sense that one starts with a vacuum, then the first non-trivial primary operator has dimension of k plus 1. So there is a huge gap between vacuum and the first non-trivial state. And this extremal conformal field theory is a very special class of the 2D conformal field theories. And then, interestingly, the modular invariance determines the whole partition function uniquely. In the sense that if you look at the k equal to 1 case, then as Witten argued that this Klein J function is unique modular invariant function, and from which one can define the JQ. And so modular invariance represents that this, once we know this vacuum contributions, then this should be polynomial function of this modified Klein-Jacobi J functions. And this A coefficient A will be fixed, and so one has to have a unique partition function. So example of partition function with small k is given here. So simplest case, k equal to 1 is given that, and k equal to 2 and k equal to 3, they are all polynomials of JQ. So extremal conformal field series is a holomorphic conformal field series with central charge 24K and has a large gap of first primary operator has a dimension k plus 1, and its partition function is given uniquely in terms of jk of tau. Now, if you look at the BTG black hole entropy from partition functions, for example, as we discussed, when k equal to 1 case, again, this AdS length scale is fixed in terms of Newton constant. And if you look at the entropy of black holes, given in terms of, again, very unique number, from which one can calculate, one can relate partition function and entropy, which is 4 pi from entropy formulas. And again, from compare with partition functions, which we heard enough about from Alexandro, one can compare this number, which is that this q minus 1 plus q is coming from vacuum, and this number coming from single black holes, and their values are very similar to each other. And this getting this relation between partition function, first non-trivial term in partition function, and the black hole entropy gets better and better in large k limit. So before one asks whether the whole this theory is consistent, one could ask whether one can get the partition function of extremal CFT direct from 3D gravities. So as theory, 3D pure gravity is very simple. One wants to calculate the thermal partition function using path integrals, for example. So one can define gravitational partition function as the integration of a metric with Euclidean action. And then usually in, say, semi-classical limit, the contribution will be given in terms of classical action times perturbative corrections around the all the stationary point of the actions. So this G star will be saddle point to solving the Euclidean equation of motion of the Euclidean gravities with given conformal boundaries. And then this should lead to the boundary CFTs given in terms of boundary Hamiltonian and chemical potential J. Now, if you look at the geometry, if you look at the AdS3 geometry in Euclidean time, then boundary is 2 torus. And if you look at the equation of motion, then geometry has to have a constant curvatures. So this geometry with satisfying classical equation of motion can be classified in terms of 2 parameters C and D integers. They are coprimes integers with C larger than 0. And they represent basically solid tori, which fills the boundary of a 2 torus tau t. And this C and D is basically characterizing the circle directions from the boundaries where one can have contractible circles. So for example, thermal AdS3 case, Euclidean time direction is compact, and BTG black hole with zero angular momentum will be spatial direction will be compact, contractible. Now, so naively one would say the gravitational partition function will be sum of all the geometry characterized by this parameter C and D, and then partition function from each geometries. So, of course, again, vacuum contribution gives you the this vacuum action contribution plus one loop corrections around the vacuum, which is given by Giombi, Maloney, and Yin. And so this will be vacuum contributions plus many other geometric contributions. So assuming the, for example, well, before we think about factorization, if you look at this sum, then it turns out to be is very badly divergent, and one needs to have some regularizations. But the zeta function regularizations breaks modular invariance and also lose Hamiltonian interpretation from the boundary series. And also, if one assumes holomorphic factorization, then one needs to think about complex geometries, which means that geometry itself is complex. Turns out, so one could make much sense out of this. One of the reasons geometry become complex is very simple. If you think about the quantum mechanics problem in Euclidean time, and if you have angular momentum, then angle variable in semi-classical limit becomes imaginary, because angular momentum is the time derivative of angle variable, and as you rotate time direction to imaginary time, angle variable has to be imaginary. So you can see the geometry where we write down the metric in terms of angle variables and maths. Then when we go to Euclidean time, metric has to be complex, not real. So some of this geometry is a bit problematic. So it became a bit tentative. Now, recently there's work by a Japanese group using supersymmetric localizations, and they have again calculated the partition function as when your supersymmetry is very small. They basically use Chern-Simon field approach to 3D gravities, where you can introduce fermionic pattern of the variables for Chern-Simon terms. Then one can use localizations. They can calculate the partition function for k equal to 1 case, but they couldn't go beyond. And also, there again, the sum of geometry remains to be an open problem. So there is c equal to 24 or k equal to 1 case, which shows that this famous monster CFT, which is G2 overfolding of the bosons compactified on Leach lattice, has the 2D CFT correspondence to 3D gravities. But one can ask whether extremal CFT exists for k larger than 1. And Matthias proposed that there isn't any such a theory when k is bigger than 42. And then there is a bit of a counter-argument by Davide. And so while k equal to 1 case, existence of extremal CFT is quite solid, it's not yet conclusive that whether such a theory exists for arbitrary k. So today we try to approach this problem using numerical conformal bootstrap. So conformal bootstrap is a technology recently have been employed quite extensively to explore the conformal field series. The main idea is study the conformal field series using associativity of operator product expansion and also unitarity. So suppose we have some phi d is a chiral operators, and you do have an operator product, then we expand it, and using this OP coefficient, and then we have this additional operators, and we sum of all the operators. But because our boundary theory is 2D conformal field theory, we included in this operator all a primary operator plus all its Virasoro descendant. Now one can introduce Virasoro conformal block, which is you start with correlation function of 4 operators, putting on two-dimensional complex plane, 0, z, 1, infinite. And then you combine 2 operators first, and then 2 operators together, then insert operator O and sum of all the operators. including the vacuums. And this quantity will be this operator, because we are using same operators, we have a square of the operator product coefficient, OP coefficient. Then we have a quantity which will, depending on central charge of theories and the conformal dimension of this original operator, conformal dimension of this operator in between, and then complex coordinate G. So this will be sum of all the operators, including the vacuum. So crossing symmetry is associativity of the OPE. So either one can combine this manner or combine that manner, and they should give you the identical answers. That leads us to a constraint on the conformal Virasoro conformal blocks. So here's the one with this quantity, and difference with basically exchanging it is replacing Z by 1 minus C. Then sum of all the operators, that has to be 0. So here we are focusing on the 4-point correlation function of an chiral operator, phi g, of the extremal conformal field series, whose dimension is lowest conformal weight above the vacuum, which is that dimension is k plus 1. And then, as we said, the extremal conformal field series has operator dimension h phi, ho has to be all the integer, and should be 0, and the k plus 1 and k plus 2 and so on. So we have this spectrum of operators. And then the question is, this spectrum is a constant spectrum of a constant conformal field theory. So that's the question we want to address. So we are assuming that there is such a theory for arbitrary k. Then for given k, we know the structures of these primary operators, and then we ask whether that is consistent with crossing symmetries. So numerical bootstrap is we want to ask. So if we know the substance, we know the dimension of the operator h phi, and then we know the distribution of ho. Then we don't know the OP coefficient. Now, question is whether if there is such a theory, then one has to have a constant OP coefficient such that that is equal to 0, which means it satisfies crossing symmetries. Now, we want to find some linear functional on these equations, satisfying that because we sum of all the operators, one of its key contribution will be vacuum contribution, and we choose coefficient this linear operator, which is a normalization such that this is positive. And then if we find linear operator such that the remaining sum, for every coefficient, because we know unitary theory, this should be positive, and if all these conformal blocks, difference in conformal blocks on linear operator comes out to be positive, and we are trying to find this such as linear functionals. And if we find it, then there's no constant conformal field theory whose spectrum is given in terms of HO. So that's our approach. So we are assuming there is such a theory, so that then we are trying to find this linear functionals such that instead of being 0, this vacuum is positive and all the remaining part is positive. Then one cannot satisfy these crossing symmetries. Right, so this equation is basically, after applying the linear operators, this is positive, because two operators always, there's non-zero identical operator can go to vacuum. So if this is positive, and this coefficient is non-negative, and this is non-negative, then if we find these linear functionals, then theory doesn't exist. So this will contradicts the bootstrap equation or this crossing symmetry equations, and that's the one people have been employing quite successfully in many other occasions. So that's the tool we are trying to use in our program. So convenient choice of functional alpha for, say, this z, we are interested in case g equal to 1/2, is that we sum of the derivative of function z, and n goes from 0 to n with alpha n. And alpha n is some arbitrary real numbers, so that we there is a bound on n. We can choose n to be as large as we want, and so we have a so basically we want to find the vector alpha from alpha 1 to alpha n, n component vector, real vector, such that vacuum contribution is equal to 1, and then all the other contributions remain positive. So if we find such alpha, then theory doesn't exist. Real. No, real, because, right, that's all we want. So any real value such that if we can make it this to be positive definite, then we are violating the equality of 0. So this problem can be translated into a standard semi-definite programming, which all of us are quite unfamiliar with. So this is a standard way. So you have a certain data, then you want to find the alphas such that this equals to 1, and that's positive definite, and the program goes around and search the alpha space such that spit out the alphas which satisfy these conditions. So there are a number of semi-definite programming solvers in the market. There are many free programs, and we are employing a SDP, SDP solver made by Simmons Dauphin. So before that, we first need to know how to compute the Virasoro conformal blocks, because we have to start with the input, which is this function, this Virasoro conformal blocks. And these Virasoro conformal blocks are independent of theories. This is just, input is just a 2D conformal field theory with central charge and dimension of the original operator and dimension of intermediate operator and complex coordinate Z. So that's completely independent quantities. And so we have to find that. Now, these conformal blocks are rather complicated function introduced by Tamalogikov. And the function form is given in this form. So it looks like extremely complicated and completely messy. And what can you do about it? How can you trust anything like this? So if you look at these functions, these things are all positive definite. And this H part is a rational function of the dimension of the intermediate operators and satisfying rather complicated recursion relations. And the functions going in this is like this. So if you haven't worked with this problem, you would pull your hair and, well, you better not do anything about it. But my young colleagues have much more courage than I do. And they managed to make a certain progress. So before that, this function h is rather complicated, but one can start from the large, this correlation function, has many interesting properties. One of it is that HMN, which appears in denominator, is always positive in the region where C is larger than 25 or equal to 25, region we are interested in. So everything became very real and very concrete in that region. And especially this recursion relation can be used to start with a seed. Recursion relation, we need a seed, and one can use the limit where C equal to infinite, where H equal to 1. Then from here, there you can feed into the these recursion relations. Now, remember that this function, we have to take a derivative of, we are not starting with these massive functions. Not only that, we have to take a derivative of this function around z equal to 1/2 n times, and you can see how difficult that will be. So, but fortunately, this function has a very interesting property. When you take an n derivative, you have a term which is positive definite and independent of derivatives, and then you have a polynomial which is a polynomial of h. So you have a derivative of f is made of the positive definite quantities with polynomial of h. And so only thing you have to concern is the polynomial of h, not this positive definite part. So that's the key thing, that whole thing looks extremely messy, but you throw it away, all this positive part, and you are playing with this polynomial part of the h. So, so here is the condition for alphas, this m vectors, such that around vacuum contribution we normalize it to be 1. Then this polynomial part of h, which we don't know its value, we know the form of the polynomials, and then we are trying to find alpha such that this is equal to 1 and this is positive, which is equivalent to say that, remember this is m vectors, and to be this to be positive definite, this has to be in, as a polynomial of h, this has to be given polynomial and dimensional polynomial, because we have a lot of intermediate vectors and some positive definite non-negative metric, symmetric matrix, 2 of them. So any polynomial can be written in this form. That's the sort of linear algebra problems. So, so the way we study central charge, we choose k to be arbitrary, and as I said, the conformal way to be k plus 1, and then extremal CFT case gap. This operator dimension will be gap, which is k plus 1 plus 0, 1, 2, 3, 4, and any value of integers. So that's the information we are using, and we know the explicit form of the polynomials. Then we are asking computer to find alpha BC such that if we find BC which is positive definite, then this is positive definite, so that we find this equal to 1, this is positive definite or non-negative. Why? Because extremal CFT, we know the light is that's the condition of the extremal CFT, that we have to have a black hole. Or right, then right, of course, but right. So one could ask, what about k plus 2, k plus 3, right? So that's equally valid. But k plus 1, we know there is operator, so we are playing with that operators. Right, so again, here there is more detail about recursion relation, how to make it use recursion relation to find the polynomial Pn. And then before we are looking at the SDP, we are just looking at whether we are making any sense of it. So we are looking at derivative of this function, this difference in conformal block with nth derivative. And then here we have to do a lot of approximations. One of is the, for example, one choose k equal to 30, and you are looking at the iterations. So remember, the h is given in terms of iterations, so you cannot have infinite iterations. So we have to many iterations. And then there's again the way we split the positive definite quantity and then polynomials. Then there is again the step of polynomials. And then if we look at the ratio of the derivative as we increase the number of iterations, it shouldn't change, right? So initially, iteration derivative will fluctuate, but at the end, the derivative shouldn't change. So this shows that as we increase the iterations, derivative remain to be 1. So this is the sort of valid region where we have a good approximation to the derivatives of the this difference of conformal blocks. And then numerical method, again, this n here, even we cannot make it infinitely discrete, so we start from +1 to some n steps, discrete integers, then we make them to be continuum. So we have a gap plus a discrete value up to n steps, and then above that we have continuum values. So we are again giving a certain constraint, and then of course the answer shouldn't be depending on this n. But as making n to be larger, you are requiring operator to be integer and in larger volume, which means more information. So you are constraining the this polynomial better. One can use different method, which led to the same answer. And here is the answer for our numerical result. So as you increase this steps we are introducing, n to be 2000. So we have 2000 discrete integer operators. And then we look at the k equals to 20 to 30, increasing 1, then k equals 40 and 70. And this in shaded region, we found the optimal solutions, which means positive definite solutions. So no, so shaded region, we look at the negative maximum values. Means in unshaded region, we have positive value regions. So if you look at the h equal to 19, we cannot find the alpha such that quantity we are looking at is positive, definite. But from h equal to 20, all the higher values, every step, we find the alpha such that this quantity remain positive, which means that, yeah. I know. Oh, this I think is like 500 and doesn't change. Right, so it's still 500 is an extremely large number. Right. Right. So that. Oh, of course. Right. So numerical. So our numerical error is like a 10 to the minus 200 or something. And that's the input you are putting into programs, so you don't know what's happening inside the programs. But we've been playing with the numbers and trying to get whether this step is rather valid. So this is right. So it looks like irrelevant, right? Right. So there is a lot of there was a lot of skepticism about our result from this special scene and so on. So we've been thinking about and playing with it. And obviously, some sense, because if you look at when we split the derivative into the positive definite part, which is independent of number of derivatives, plus you have polynomials, and then there is unknown also, unknown positive definite OPE, which is decaying exponentially. So that makes it, even though we find the definite positive values, whether there is enough of those things which is errors creeping in and makes it positive definite. Of course, that's of course we are aware of that possibility, and we've been trying to figure out the weight, where is the errors, where is the contributions, and that is. Right, rhetorically, right. Hmm? Right. Right, but the global blocks has less information, so. Right. I think if it. Oh, right. Right. So some sense we are asking some sense the computer too much in the way that maybe errors are slipping in and then add the positive definite instead of the so. But the way we've been trying to understand that is the tweaking the, for example, n and whether there is some coherent, consistent behavior appearing, and that's what we are finding. But still, we are still playing with this problem because obviously, if you add too much and the errors are slipping and the errors are tails are dominating head, then that doesn't make sense. So, right. No. Right. So negative maximum values are found. So right. So shaded regions are allowed and the white regions are excluded. Right. Right. Well, up to 20, but that's not part of the game. So instead of k plus 1, k plus 2, then right. Right. So if you start with gap, you can adjust the gaps to be, say, instead of k plus 1, if I say k plus 2, then that's right beyond the BTG, little bigger. So that you record. So it's more than extremal, not over extremal series. Right. Modular. Yeah. No, but modular invariance has say has to be k plus 1. So no. Oh no. Right. 3-point function. Right. One could have a right vacuum then k plus 2. Right. So that could be interesting possibilities. So as we say, error is 10 to the minus 200. So, and our result, numerical result, as suggests the extremal CFT may not exist as a constant theory for k larger than or equal to 20. So to summarize, no extremal conformal theory for k larger than 19. That's our numerical result suggests. So pure 3D gravity may not exist as a constant quantum theory at weakly coupled space, which means large k means small cosmological constant. under the assumption of holomorphic factorization and modular numerical errors. And near extremal CFTs, where the gap starts at K, we run the numerical analysis, and it's a little more delicate and it needs to analyze it further. All right, thank you.
This may be slightly off your main point, but the assumption that there is a holomorphically factorized theory dual to weakly coupled pure gravity, I mean, that's pretty old now, the assumption by Witten. I was just wondering whether there are other reasons to revisit it. For example, this argument that chaos, that somehow CFTs dual to weakly coupled gravity should exhibit chaos, they should not be rational, and so on. I mean, is this Witten conjecture still, does it still sound as convincing as it did?
Oh, I'm not quite sure about. I'm not quite sure this chaotic behavior and story with weakly coupled gravities. I've been hearing about it from people, but I don't know the relevance to.
Well, the claim is that if it's not, doesn't exhibit, if it's rational, doesn't exhibit the chaotic behavior which you need to compare with weakly coupled gravity. And so somehow, I don't know how, if I'm stating it fairly.
I think that's what helps.
But so you mean without having, even with having all exponents be rational, and in fact in this case integer? Yeah, it's confusing me right now. Yeah. Okay, maybe we can discuss it.
All right, thank you.